and 2 equals 2. None of the others show that equality. Okay? So everybody okay on that? All right, next one. Vector operations. So we need to learn how to add, subtract, and multiply. And the kind of multiplications that we will do is very simple. There are two kinds of multiplications. One's called scalar multiplication, and the other one's called vector multiplication. We shall not do vector multiplication. We'll do only scalar multiplication. So a scalar is a mere number, a mere mortal. Okay, like me. Just a simple old number. Compared to a vector. What's a vector? Or a pair of numbers, right? If you think about it in component form, it's a pair of numbers. A scalar is a single number by itself, okay? So the kind of multiplication we'll do are what are called scalar vector multiplications, not vector multiplications. And here's the definition of scalar multiplication. So let me get this snipped and then we can talk about it. Okay, so I'm going to do an example. So you're given u as this vector, and you want 2 times u, and we've kind of used this in in the examples that Laura was asking me. Okay, we kind of did that, but we did it in a geometrical fashion. Here we're going to use component notation. So then this would become negative 6, 4. Pretty simple stuff. Pretty simple stuff. Okay, you just multiply each component by whatever the number. So this is a scalar. Okay, that's a scalar. How can I tell that that's a scalar and this other guy is a vector? How can I tell that? What's the difference between a scalar and vector in terms of writing it? Vector is going to be bolded. So you can easily have a vector like this. What do you think A would be? A scalar. Okay, so please make sure you know this notation, okay? That's the whole reason why I emphasize the bolding operations on these things, okay? All right, next example that I want you to do, you're given V is equal to that. Give me W equals minus V, which is the thing that we did in that geometry problem a minute ago, Laura. So give me minus V. So V is minus 3, 5. W is minus V. What's W equal to? Evelina. What's W equal to? Sorry? What? What's the scale? So if I gave you this equation here, what's the scalar in here? Negative 1 is a scalar. This guy is a scalar. This guy is a scalar right there. So all you need to is times all this thing by a negative 1. So you get 3, negative 5. Okay? So everybody okay on that? That's scalar multiplication. Sorry? That's a V. Where's the Y? I don't see. No, that's a V. That's why I rewrote it here. I rewrote it there. Yeah. Okay? All right, so scalar multiplication, easy stuff, right? Yeah? Chewy? Let's not worry too much about the geometrical way of doing it. I'm not too fond of it. Vector addition. So get these rules down for vector addition, and then let's go do some examples, okay? Oh, shoot. Sorry, say it again. 3. Is that right? Well, let's have someone come up to the board and do this then. The answer here is negative 1 comma 11. Okay? Okay, subtraction. Okay, I'm going to let you guys kind of read this and follow through. Okay, so I'll pause this here for a minute. Next concept, I think. Properties of vector operations. I'm going to just let you read this on page 428. Okay. So these are properties that you learned in grammar school, except it works for vectors as well. Okay. For vectors. So read the stuff on page 428. Okay. All right. Next concept. Okay, direction angles. So this is what I told you. We're going to talk about in order to talk about how we talk about the direction of a vector. So there is the definition there, okay? The direction angle is the angle a vector makes with the positive x-axis. So that would be this angle here. That's the direction angle. Okay? With the positive x-axis. So you can see why this is this vector stuff is in the trig chapter, because you got angles, and pretty soon we're going to come up with some trig. Okay, pretty soon we're going to come up with some trig. All right, everybody got this down? Okay. So that was kind of just a picture. Here's the mathematical formulation for how you find that angle. Okay. This should look very familiar to you. Should look very familiar to you. Should look very much like what we did with complex numbers. Right? Looks very much like complex numbers. Okay, remember in a complex number we had something like z is equal to a plus bi, and then the angle was theta equals tangent inverse b over a. Well, here's the formula over again, except it's for vectors. Except it's for vectors.